Hello Finxters, I hope you're doing great and welcome to another episode. This time we'll be talking about Base64, which is a common way of converting digital content or binary content to text, which is easily transferable via an email, or even if you want you can print it out, send it to someone, and this other side, the recipient, will be able to actually just retype the content you sent him, and it will be able to recreate the binary content on his computer. I will show you how I implemented this solution, although there are various ways to do it. I did it as a Python class, and this class has several important parts which I'll explain for you to facilitate easier understanding of the process. The first thing is this sequence of characters. There are 64 of them. That's where Base64 got its name, and each of them has its index or its sequence number. It's 0 for A, 1 for B, and all the way to 64 for this slash. Of course, these indices are written, will be referred to internally as a 6-bit number, binary number. So just keep this in mind, and we'll get back to that later. I have also defined this padding symbol as 0, and next what we have is a method for slicing the original data into chunks of predefined length. Here we get the original data, here we get the length, and what this method produces is an array of data chunks or segments of predefined length. The method encode takes the original data, sets the padding length to 0. Padding length represents a number of padding symbols that have to be added on the original data to make it compatible with 3-byte length. So in case we have only or if our original data is only 1 byte in length, 2 more bytes of this symbol 0 will have to be added to be appended on the end to make it 3 bytes in length. Of course, our data can be much longer, and it usually is, but it has to be divisible by number 3. It has to be, if we imagine our original data, it has to be formed as a sequence of blocks which are 3 bytes in length. Why 3 bytes? Well, you can read more about it in the article. However, the short explanation is 3 bytes or 24 bits is a length of a block that is divisible both by 6 and by 8. It has to be divisible by 6 to facilitate converting each of these 6-bit segments to one of the letters here in our chars object, in our array, and it also has to enable splitting when we decode. When we encode our data, we have to be able to take byte by byte, because that's the way the data is stored in a computer, in a computer's memory. Here the method calculates the length of the padding. What it does, it actually determines how many padding symbols should be added to the original data, and this can mean 0 symbols if our data is is multiple of 24 bits or 3 bytes. It can be 1, or it can be 2 symbols appended to the end. In the next step, after we completed our data in terms of making it a multiple of 3 bytes, it gets split to 3 byte chunks by calling this method here. In the following step, we have to take our data and make it representable in a binary form. For that purpose, we will take each chunk of our 3 byte segment, each 3 byte segment of from our array, which this method returned, this method chunk returned to this array. And for each of these chunks, we will take byte by byte, and we will convert it to a string that will actually represent our bits in this byte. And this is why I call this object binary or bin string representation. After that step, after this step was finalized, we will have our binary string representation containing all our original data, and here we will call this chunking method once again, and we will split this binary string representation into chunks of 6 bits in length. Now that we have done that, we will take each of them and just remember what I said in the beginning. Each of these characters has its index, and this index is actually represented by this 6-bit element. And now that you take, for instance, first 6 bits from our binary string representation, which might say 000 000, that would point to this character A. And one by one segment of 6 bits, our original data would get converted to this Base64 encoded string. Since we have padded our original data to full 3 bytes, possibly if it was not a multiple of 3 bytes, we have also actually made up this last character, which we didn't originally have. So to compensate for this padding, we will take all the original bits and up to number of padded symbols, and we would now replace these padded symbols with this symbol equal. You can notice that we don't have it in our original table of symbols, and we would just put this in place of a padded symbol or character to denote that when you take a Base64 encoded string, you can notice right away that it has 1 or 2 symbols that are padded to make everything fit. There is another method in this class, and it's called decode. It's meant for decoding Base64 encoded string and converting it back to its original form or original data. It works by counting how much padding do we have in our Base64 encoded string. it will replace it by actually any symbol from our input table. I've chosen for practical purposes to make it a symbol A, because if we take, for instance, symbol A, then we know that when we convert this string to this character back to the binary string representation, we know that it will be replaced by 6 zeros, because 6 zeros represent a 6-bit index for letter A. And since we don't have this symbol of equality in our original table of characters, the algorithm wouldn't know how to represent it in binary form. Now that we have processed our data in terms of replacing this padding character with something that we can actually encode in binary form, for each of these characters in Base64 encoded string that represents our data, we will reconstruct a binary string by formatting, by using this formatting syntax, and we will take each character, calculate its index in this chars array, and format it as a binary string. The next thing we'll do, we'll take our binary string, the freshly created one, and we'll split it in 8-bit chunks. So remember, before we did that, our binary string was a string of zeros and ones, which were produced as a sequence of indexes of the original characters. Now that we are going in the opposite direction, we will just take each 8-bit chunk and we will convert it to we will actually just take it as a 1 byte. Here we initialize some object, Base64 decoded string actually, that will contain our original data. When I say original in this context, I mean on data that was actually fed into the algorithm originally. So it was this binary content all the way in the beginning of our story. And for each chunk in our array of 1 byte chunks, we will take this chunk, all 8 bits of it, interpret it as a binary form, as a number in binary form, and convert it to an integer, and we will just append it as a byte to our Base64 decoded string. Finally, we will trim as many padding symbols as were appended, and we know that because we counted the number of these equal symbols in the beginning. So if we had one symbol of equality, we would just get rid of this last 1 byte, or if not, if we had 2 symbols, we will discard the last 2 bytes, or if we didn't use padding at all, we already have our Base64 decoded string, and we are returning this object to the calling function. You can notice that at first, now we are looking at let's say the main function. First we got a product of encoding our initial string and stored it in Base64 encoded object B64 ends. We printed it out, then we fed it once again into decode method, and once it got decoded, it should be the same as this string we started with. To prove this, I will start this program and show you that it works correctly, and this was our Base64 encoded string, and it had one symbol for padding in it, and when we decoded it, we got just what we started with. Finxter rules, as always. I'll finish today's episode on that note. I hope you managed to have some fun to figure out how the algorithm works, and I repeat, it can also be implemented in different ways. I chose this one because I wanted to have everything self-contained in a class, but you can also do it as a script or maybe in some other way. I'll leave that to your imagination. However, you also have the article. I encourage you to read it and fill any possible holes in your knowledge that maybe I didn't cover during this exposition. However, if you need to, you can go through this video once again and read the article, and I'm sure you'll be able to understand how Base64 works. I mean, it's a really simple algorithm. It just takes the input, it takes it as a sequence of bytes. It takes the sequence of bytes as segments of 6 bits, and it just matches for each of these 6-bit sequences a symbol that was predefined in this table of symbols or characters. And on its way back, it will take every symbol. Now we are talking about text. It will take every textual symbol, find its 6-bit binary representation, put together in a sequence all these 6-bit representations, resegment them as 8-bit segment representations, and put them all together, and just display what the decoder produced. And it should absolutely always be the same thing as the one that was initially put in the encoder. That's it from me for today. Until the next time, see you.